So today we will discuss about two important concepts of chemical kinetics. One is molecularity of the reaction and the other is the order of the reaction. So first let us understand the concept of molecularity. Okay, so let us take two examples, two chemical reactions, 2A plus 3B giving products. Okay, this is one reaction. The other reaction is A plus 2B giving products. Okay. So by looking at the stoichiometric equation, let us try to predict what would be the empirical rate law. Okay. So let us try to guess what would be the rate equation or rate law by looking at the stoichiometric equation. So what do you mean by rate law? Rate law is nothing but writing the rate in terms of rate constant and the concentration of the reactants. So for the first chemical reaction, dx by dt, that is the rate of the reaction, is equal to rate constant K into concentration of reactant A, which appears twice in the reaction, so A square into concentration of B Q. Okay, so this is the empirical or the predicted rate equation or rate law for the first reaction. Okay, for the second reaction, it would be dx by dt is equal to K, the rate constant for that particular reaction, into A to the power 1, because the reactant A appears with a stoichiometric coefficient of 1 into concentration of reactant B square. So if you carefully look at these two equations, you can understand the relation between the rate and the concentration of the reactants. How does rate depend on the concentration of the reactant? So the dependence of the rate of the reaction on the concentration of A in the two reactions are different. Similarly, the dependence of the rate of the reaction on the concentration of B is also different. Here, if you carefully look and try to answer yourself, okay, in which case the concentration of reactant A has more effect on the rate of the reaction. Similarly, in which case concentration of reactant B has a larger influence on the rate of the reaction. The answer is obvious. It is the first reaction. Why? Because in the first reaction, this concentration term for A appears two times, whereas here it only appears once. Whereas in the similarly in the first reaction, concentration term B appears three times, whereas here the concentration of B appears only two times. So both the reactants A and B has a larger effect or influence on the rate of the reaction in the case of first reaction. Let me try to uh, expand this argument in a much detailed way. Okay, I'll give an alternative explanation. Suppose if I double the concentration of reactant A in both the case, what will happen? If I double the concentration of A in the first case, so it becomes 4 times, the rate becomes 4 times, because if I double this number, again you have square, so 2 square is 4, so the rate becomes 4 times. Whereas here, if I double the concentration of A, that is if I double this number, rate also gets doubled. So the concentration of A has a greater effect on the rate in the first case, because both the cases you are doubling the concentration of A, but in the first case the rate becomes 4 times, whereas in the second case rate becomes only 2 times the earlier rate. Similarly, if I double the concentration of B in here, so this value becomes 2 times, so whole cube, it means the rate increases 8 times. Whereas here, if I double the value of B, so it becomes 2 square, that is rate only increases 4-fold. So again, concentration of B has a greater influence on the rate of the reaction in the first case. Now, how many if I ask this question, so in which reaction the reactants overall has a larger effect on the rate of the reaction? The answer is again the first case, because here altogether 5 concentration terms are involved in the rate equation, whereas here only 3 concentration terms are involved in the rate equation. So altogether in the first case or in the first reaction, the concentration of reactants has greater effect on the rate of the reaction compared to the second reaction, because here only 3 concentration terms are involved altogether, whereas here 5 concentration terms are involved. Say for example, if I give another reaction, A plus 2B plus 3C giving product, then what would be the empirical rate equation? It would be dx by dt is equal to K into concentration of A to the power 1 into concentration of B square into concentration of C cube. So if I compare the individual reactants, okay, A has a similar effect in the second and the third reaction, but A has a greater effect in the first reaction. If I compare these two reactions, concentration B has same influence on the rate of the reaction, whereas in the first equation the concentration of B is more because it's appearing 3 times. Here you have one more additional reactant term C, which also affects the rate of the reaction, but here since reactant C is not involved in these two reactions, it does not affect the rate of the reaction. So altogether, how many molecules of the reactant or how many concentration terms of the reactants affect the rate? The answer is 6. So out of the 3 cases, in which case the reactants has highest effect on the rate of the reaction? The answer is here, because there are 6 concentration terms. And in which case the reactant has least effect on the rate of the reaction? The answer is this, because only 3 molecules of the reactants are involved. So these numbers are very important whenever you are studying a chemical reaction. Okay, identifying this number is very important, because from that we can come to know what is the exact effect of all the reactants on the rate of the reaction. The number that I have written in each case, it is nothing but called as molecularity of the reaction. So let us define molecularity of the reaction. It is the total number of molecules of the reactant involved in the balanced chemical equation. So the definition is very simple. It is the total number of reactant molecules involved in a balanced chemical equation of the reaction. Balanced chemical equation of the reaction. So what is the molecularity of this particular reaction? How many molecules of reactants are involved? 2 molecules of A and plus 3 molecules of B. So the molecularity of this reaction is 5. What is the molecularity of this reaction? 1 molecule of A and 2 molecules of B. So the molecularity of the reaction is 3. Only 2 types of reactants are involved, but altogether how many molecules are involved? 3 molecules. So molecularity of the reaction is 3. Whereas there are 3 types of reactants involved here, but the molecularity of the reaction is 1 plus 2 plus 3, that is 6. Molecularity is 6. What do you mean by molecularity is equal to 6? It means 6 concentration terms, okay, of the reactants is affecting the rate of the reaction. So if I take a reaction, A molecules of A plus B moles of B giving product, how will you write the rate equation? The rate equation, the predicted rate equation is dx by dt is equal to K into concentration of A to the power A into concentration of B to the power B. So what is the molecularity of this reaction? The molecularity of the reaction is A plus B. A plus B. If I give you another example, okay, A plus half B giving product. Okay, while predicting the molecularity of such reactions, okay, even though this reaction may be in a balanced chemical equation of the reaction, we will not calculate the molecularity by using this form of chemical equation. We will try to avoid this fractional numbers because half molecule, okay, does not make any sense. We can have integral number of molecule, one molecule or two molecules. We cannot have fractional number of molecules. So we will change this, modify this balanced chemical equation by multiplying this equation throughout by 2. So the equation is 2a plus b giving product. 2a plus b giving product. So what is the molecularity of this reaction? The molecularity of this reaction is 2 plus 1 is equal to 3. So remember, even though this equation is balanced, we will not calculate the molecularity of this reaction. Okay, we have to convert it into a suitable form and then calculate the molecularity of the reaction. Let me give you one more example. N2 plus H2 giving NH3, that is production of ammonia by using nitrogen and hydrogen. Again, remember here, when you are calculating the molecularity of the reaction, it is very important to note that whether the reaction is balanced or not, because molecularity of the reaction is nothing but the total number of molecules involved in the balanced chemical equation. But this equation is not balanced, so we have to balance this equation. This is okay, we have to balance this equation. N2 plus 3H2 giving 2NH3. Now the equation is balanced. Now you can calculate the molecularity. The molecularity of the reaction is 1 plus 3 is equal to 4. So altogether 4 reactant concentrations are affecting the rate of the reaction, which is very high. So you can expect that you can play with the rate of the reaction. You can alter the rate of the reaction, okay, significantly by changing the concentrations of either one of the reactants. Which concentration has greater effect? Hydrogen concentration or partial pressure, because all these are gases. The partial pressure of hydrogen has a greater effect on the rate of the reaction because there are because you have the stoichiometric number 3 compared to nitrogen, which has a stoichiometric number 1. So hydrogen has a greater influence than nitrogen. So this is the definition of molecularity of the reaction. And if you carefully look at all these examples that I have given here, the molecularity of the reaction is always a whole number. It is always an integer greater than 0. Okay, you cannot have a molecularity, a reaction with zero molecularity. What does it mean? What does it mean? A zero molecularity reaction? It means no molecule is involved, which is not possible. So molecularity of the reaction is always greater than 0. It is a positive number and it is a whole number. It is an integer. Okay. So the main purpose of introducing the concept of molecularity of the reaction was to understand what is the exact effect of the reactant concentrations on the rate of the reaction. But the molecularity or the application of molecularity or the utility of molecularity did not stood up to its to its expected to its expectation. Okay, why? Because it has very important limitation. So what is that limitation? Let us try to understand. Suppose, okay, you have a chemical reaction A plus 2B giving product. You know that a chemical reaction in most cases does not take place in a single step. So this chemical reaction also, though the stoichiometric equation or the balanced chemical equation looks simple, appearing that the reaction takes place in a single step, this may not be so. Okay, so this reaction may be a complex reaction taking place in several number of steps. Let us assume that we already know what is the mechanism of this reaction. So I will give one random mechanism. Okay, so let us assume that this reaction takes place in two steps. This reaction takes place in two steps. In the first step, one molecule of A reacts with one molecule of B to form some intermediate species called X. And in the second step, this X reacts with the other molecule of B, another molecule of B, resulting in the formation of the final product P. If you add these two, the overall reaction, okay, will be A plus 2B giving product. Okay, because X term gets cancelled, so you get A plus 2B giving product, which is nothing but the balanced chemical equation. So this reaction actually takes place in two steps. And in my earlier class, I already informed you that all the reactions proceed with the different speeds. That is, the rate of reactions, different reactions are not same, they will be different. Why they will be different? Because the nature of the reactant molecules involved in each step is different. So the rate of the first step will be different from the rate of the second step. Let us assume that the first step is relatively slow compared to the second step. So the second step is much faster compared to the first step. So the question arises here, which is therefore the rate determining step. So which out of these two is the rate determining step? What do you mean by rate determining step? That particular step whose rate has a greater effect on the overall rate of the reaction. The answer to this, okay, it is abbreviated as RDS, rate determining step. So which step is the rate determining step? The slowest step is always the rate determining step. Why the slowest step is the rate determining step? For that I will give an analogy. Okay, so if you are in a competition, okay, a relay, 4 into 100-meter relay, you have four athletes A, B, C and D. Out of four, three athletes uh, are very good. Okay, so they run very fast, whereas one of the athlete is relatively slower. Okay, so the overall result of the competition, that is whether that particular team wins or not, is decided by the slowest runner or the slowest athlete, because with whatever speed the first three athletes run, their effort will be subdued, or their effort will be reduced. The chances of their victories will be reduced because of this person or the athlete who is very slow. So he is the one who will decide what is the outcome of the race, whether they will win or lose. Okay, so similarly the overall rate of the reaction depends on the slowest step of the reaction. It is just like in the traffic. Okay, so behind you have vehicles which are capable of moving with greater speeds, but in front you have a lorry, okay, which moves very slowly. So though the vehicles that are behind this lorry has the capability of moving with greater speeds, but their speed is controlled by the lorry which is ahead of them. Okay, so similarly here, though the other steps are very fast, the overall rate is largely affected by that step which is very slow. That is called as the rate determining step. So when we are writing the rate law or rate equation, it is now clear that we should not consider the overall reaction. We should only consider the rate determining step or the slowest step involved in the reaction for writing the rate equation or the rate law. Therefore, the rate equation or the rate law for this particular reaction is dx by dt is k into concentration of A into concentration of B. What is the empirical rate law or the rate law that we had guessed from the stoichiometric equation? It is dx by dt is equal to k into concentration of A into concentration of B square. This is the expected, this is the true rate equation or rate law. So if you look at them, they are not one and the same. Okay, the effect of or the influence, sorry, the influence of reactant A on the rate is same, predicted by the empirical rate law as well as the true rate law. But if you compare the effect or the influence of reactant B, they are different. So according to this reaction, three concentration terms are affecting the rate of the reaction, but the reality is only two concentration terms are affecting the rate of the reaction. So even though the molecularity of this reaction is 3, that is, we are assuming that or predicting that three concentration terms are affecting the rate of the reaction, but actually only two concentration terms are affecting the rate of the reaction. Okay, so why this problem arises? Because most of the chemical reaction does not take place in a single step. Suppose this reaction, okay, proceeded in a single step, then this molecularity would have predicted the correct rate law, that is three concentration terms affect the rate of the reaction. But in most of the cases, since more number of steps are involved in a chemical reaction, it is very hard to find out exactly how much concentration terms are affecting the rate of the reaction. I'll give you one more example. Okay, A plus 2B plus C giving product. You have some reaction, okay, and let us assume that we know what is the mechanism of this reaction. This also takes place in several steps. In the first step, A plus B gives some intermediate X, maybe one intermediate or more. In the second step, another molecule of B reacts with intermediate to give one more intermediate Y, and in the third step, this Y reacts with the molecule of C to yield the final product. So this reaction takes place in three steps. Okay, so if you combine all these, so X gets cancelled, Y gets cancelled, you get A plus 2B plus C giving product, okay, which is nothing but the overall reaction. So you have three steps involved in the reaction, and because the nature of the reactants are involved in each steps are different, the rate of the reactions should also be different for the three steps. And let us assume that this is the slowest step, okay, out of the three. So this is nothing but the rate determining step. So what is the molecularity of this reaction? Molecularity of this reaction is 4. 1 plus 2 plus 1, that is 4. So we are, by looking at the balanced chemical equation, we are assuming that 4 concentration terms are affecting the rate of the reaction. It means the reaction is highly influenced by the concentration terms. Okay, even if I alter the concentration terms by a little amount, it has a great effect on the rate of the reaction. But the reality is only one concentration term affects the rate of the reaction. This X is an intermediate. You have only one original reactant involved in the reaction. So it is actually only one concentration term that affects the rate of the reaction. So there is a difference in the prediction made by molecularity. Okay, suppose if it was a single step reaction, this concept of molecularity would have predicted the correct effect of concentration on the rate. But since this reaction takes place in several steps, the expected answer and the predicted answers are completely different. So this is one of the important limitation of molecularity. So here we introduce a concept called as order of a reaction. So what is order of a reaction? Order of a reaction, okay, it can be said in a very simple way. It is nothing but the molecularity of the slowest, that is the rate determining step of the reaction. It is the molecularity of the slowest step of the reaction. This is one way of defining the molecularity. So if I take this example, what is the molecularity of the overall reaction? It is 4. But what is order? It is the molecularity of the slowest step involved in the reaction. What is the slowest step here? Which is the slowest step? The second step is the slowest step. And how many molecules of the reactants are involved here? Only one molecule. So molecularity of the slowest step is 1, because only one molecule of the original reactant is involved. So the order of this reaction is just 1. Okay, so what does it mean? That is only one reactant concentration, that is one concentration of B, one term of concentration of B has an effect on the rate of the reaction. Suppose the first step was the slowest step. What is the molecularity of this step then? It is one molecule of A and one molecule of B. So the order of the reaction would have been 2. What does it mean? There are two concentration terms which affect the rate of the reaction. Which two concentration terms? One concentration of reactant A, one concentration term of reactant B. So order of the reaction is nothing but the molecularity of the slowest step involved in the reaction. Or you can also define order as it is the sum of the powers to which the concentration terms are raised in the experimentally obtained rate equation. Okay, it is the sum of the powers to which the concentration terms are raised in the experimentally determined or obtained rate equation. So how did we predict this mechanism? By doing some experiments. Okay, we had obtained this mechanism. So this is an experimentally determined mechanism, and which is the rate equation, the rate equation for this reaction. The rate equation is the second step, that is B plus X giving Y, which is the slowest step. So the rate equation, that is experimentally determined rate equation is now dx by dt is equal to k into concentration of B to the power 1. Okay, so since you have this power 1 here, okay, it is the power to which the concentration term is raised in the experimentally determined rate equation. The order of the reaction is 1. Suppose if this step was the slowest step, then how would you have written the rate equation? Okay, if this was the slowest step, this would have been the experimentally determined slowest step. In that case, the rate equation would have been dx by dt is equal to k into concentration of A to the power 1 into concentration of B to the power 1. So this is the experimentally determined rate law if this was the slowest step. So then what would be order of the reaction? It is the sum of the powers to which the concentration terms are raised. So 1, that is the power to which concentration term A is raised, plus 1, that is the power to which the concentration term of B is raised. So the total order of this reaction would have been 2. So remember, order of the reaction predicts the exact effect of concentration on the rate of the reaction. Why? Because it is not a predicted quantity, it is actually an experimentally determined quantity. Now you should understand one thing. Okay, if from some experimental results you are possible to predict what is the mechanism of the reaction, and from the mechanism if you identify which is the slowest step, then it is possible to find out what is the order of the reaction. The same holds good on the in the reverse side also, vice versa also. Suppose if you know what is the order of the reaction, you can predict or you can propose a mechanism for a reaction. How? Let us see. Okay, suppose if I have a reaction A plus 3B giving product, some reaction A plus 3B giving product. Okay, what is the molecularity of this reaction? The molecularity of this reaction is 4. But what we have observed is the experimentally determined order is 2. So even though molecularity of the reaction is 4, which is predicted by looking at the balanced chemical equation, the order of the reaction is just 2. This is experimentally determined, and out of that it is actually 1 plus 1, that is order of the reaction with respect to reactant A is 1, order of the reaction with respect to reactant B is also 1. So the total order of the reaction is 2. So definitely this is not a reaction taking place in a single step, because molecularity and order, they are not having the same value. So let us propose a mechanism. Okay, that mechanism may be true or false, that I don't know. It may be a correct mechanism or it may be a wrong mechanism, but I can propose a mechanism from which I can deduce that the order of the reaction is 2. So I will propose a mechanism based on the previous chemistry knowledge I have with these reactions. So I am proposing a mechanism that in the first step, one molecule of A and B react with each other to give an intermediate X. In the second step, this X reacts with two molecules of B to give the final product. So what is the overall reaction? X gets cancelled, you get A plus 3B giving product. So this is one possible mechanism. You can give 100 possible mechanisms, but this is one possible mechanisms that I am giving, okay, based on previous chemical knowledge about this reaction. Now out of these two, this should be the slowest step. Okay, this is faster and this is the slowest step. Since this is the slowest step, this is the rate determining step. So the overall rate of the reaction should be written by looking at the rate determining step, that is dx by dt is equal to k into a to the power 1 into b to the power 1. So what is the order of the reaction? Order of the reaction is 1 plus 1, that is 2. That is 1 with respect to reactant A and 1 with respect to reactant B. That is nothing but the experimentally obtained order. So this mechanism is possible to explain the second orderness of this reaction. But you can propose another mechanism which is completely different from this, in which, okay, you can get a second order reaction. Now one third person may give one more mechanism which is different from the first two mechanism and prove that for that mechanism also the order is 2. So in such cases Based on this data, it is highly impossible to tell what is the correct mechanism. Then in such cases, we have to go for other methods, complementary methods that you have studied for determining the mechanism, such as spectroscopic method or uh, tap, uh, trapping of intermediates. There are different methods from which you can find out what is the correct mechanism. But remember the order of the reaction. By using this data of order of the reaction, it is possible to predict what is the mechanism of the reaction. But by just using this data alone, it is impossible to predict the mechanism. You require some assistance from other methods, complementary methods also, by using which you can predict what is the mechanism of the reaction. Okay, so at least you can uh, reject some of the mechanisms, wrong mechanism. If not, you can predict what is the correct mechanism exactly. At least you can predict which mechanisms are not correct. Okay, this is the advantage of order of the reaction. Now let us understand what are the important differences between order and molecularity of the reaction. So the first difference is the definition. What is molecularity of the reaction? It is the number of reactant molecules in the balanced chemical equation of the reaction. Definition of molecularity. Whereas, what is the order of the reaction? Order of the reaction is the molecularity of the rate determining step or the slowest step involved in the reaction. Okay, or you can use the alternative definition. The second important difference is the molecularity of the reaction. Molecularity is always greater than 0, and it is always a whole number. It is always an integer. It cannot be fraction. It cannot be fraction, and it is always positive, greater than 0. Whereas order can be negative or positive. It can be 0. We have several zero ordered reactions. It can be even a fraction. So order of a reaction, it can be positive or negative. It can be even 0. It can be even fraction. Okay, as the things reaction gets complicated, you will see that in some case order becomes negative, it becomes 0, or it can be even a fraction. Okay, the third important difference is molecularity is obtained by looking into the balanced chemical equation. Okay, it is an empirical value. It is obtained by just looking at the balanced chemical equation. But what is order? Order is very important compared to molecularity. Order is very important because it is an experimentally determined quantity. By doing experiments, we have found out the value of order. So its value is very important or very significant in chemical kinetics. The fourth difference, and which is also a very important difference, is using molecularity we cannot predict mechanism, whereas why order is important, determination of order is very important, because uh, we can predict mechanism of a reaction, okay, but not just by using this one method. We require some supplementary or complementary method, okay. One can predict what is the mechanism of a reaction by using order, okay, and vice versa, that is, if you know the mechanism of the reaction, we can determine or find out what is the order, or if you know what is the experimentally determined order, okay, then it is possible to predict what is the mechanism of the reaction. So these are the important differences between molecularity and order. But since molecularity is just an empirical number, it is not an experimentally determined number, and it has its own limitations that I discussed here, and it has no uh, utility in determination of mechanism of the reaction, whereas order has several advantage and it is an experimentally determined quantity. So we will further not study any concept based on the molecularity of the reaction. We will be discussing about the rate of the reaction or about chemical kinetics of a reaction in terms of the order. So this is about the order and molecularity of the reaction. Thank you.